Solution to the acid-base series, we are going to solve this problem where we are given 3 carbon ions A, B and C. So let's give them some name A, B and C, and the pKa values of their respective conjugate acids are given as 41, 33.4 and 31.5, and we are supposed to explain this trend, that why pKa is decreasing for the conjugate acids of A, B and C. Okay, now in order to solve this, one thing to remember is that pKa is inversely related to Ka, which is the acid strength. Ka means acid dissociation constant, which represent the acid strength. So one with a bigger value of pKa will have small acid strength. Okay, will be less acidic. It means the acid strength is increasing as we are going from A to B to C for the conjugate acids, and we need to explain this. Okay, that is one thing. Second thing is, since the pKa's are given for the conjugate acids, so we should write the conjugate acids for A, B and C and see what is the driving force for the reaction. So the conjugate acids and bases, they differ by 1 proton. So the conjugate acid of A is this, which is toluene. Conjugate, so this loses a proton and some base is there, so this loses a proton and forms A. Second one is, you have diphenyl methane. So diphenyl methane loses a proton and forms B. Third one is triphenyl There are 3 phenyl rings in the third one. It loses a proton Okay, now in order to answer this problem, we need to look at the stability of the bases A, B and C. Why? Because we know that reactions goes towards stability. They are driven by stability. So the species which is more stable is formed more readily as compared to the species which is less stable. Okay, so if we look at A, so I'm talking about A now. So looking at A, we know that for a carbon ion where the carbon bearing the negative charge is in conjugation with the ring. So this charge is in conjugation with the ring electrons. Okay, so they all are in the same plane, so they can get delocalized. Fine. So what we get is, we get the resonating structures for this one, CH2, a negative charge here, double bond, and then on similar lines we can draw the other resonating structures. Negative charge, negative here, fine. And then this, and what you get is the fourth resonating structure. Charge here, double bond here, double bond, CH2, electrons move here and then onto this. So what you're getting is a double bond, double bond, double bond and CH2 negative. So these all are the resonating structures for A. So what happens because of this resonance, there is the delocalization of the charge. And we know that the greater the delocalization, the more is the stability of that species. Greater delocalization means greater stability. Why? Because the charge gets delocalized, gets spread. It's not intensified at one place. Okay, so greater stability. So based on that, A is stable. Okay, but our aim is to compare the stability of A with B. So in case of B, we have two phenyl rings attached to the carbon bearing the negative charge. So we have two phenyl rings. We have two phenyl rings in the case of B. So this is B. Okay. So we have two phenyl rings in the case of B. So if I write it here again. So there are two probabilities, or there more probability of delocalization of the charge. One of them is like this, okay, and then it spreads onto the whole of this ring which I'm putting in green, okay. And the other option is that this negative charge gets delocalized onto the second ring, okay. So both are equally probable and both happen, so B, okay. So because of which there are more number of resonating structures than A, because now there are two phenyl rings which are involved in the delocalization. So it means B has more resonating structures, more delocalization, greater stability than A, right? So it means B is more stable than A. So if B is more stable than A, then this equilibrium for the second one, it would be more towards the product side as compared to towards the reactant side, okay. So if you look at the arrows, I have drawn that the forward arrow lengthier as compared to the backward arrow, fine. So this explains that since B is more stable than A, B is more stable than A, so B, this equilibrium is more towards the right hand side. So the diphenylmethane wants to lose the proton because the product which is going to form is much more stable as compared to the toluene, where you lose a proton and form a carbanion which is less stable than B, okay. Now for the third one, which is this one, so if I give them the names 1, 2 and 3, for the third one there are three phenyl rings. So we expect a cumulative effect, like there are three phenyl rings, so its acidic strength or its tendency to lose proton is even more as compared to 2, okay. So its acidic strength should be more. And if we look at this, yes, the acid strength is increasing because the pKa value is decreasing, okay. So pKa value is decreasing, acid strength is increasing. That answers one part of the question. But the important question in the question itself is that when you go from 1 to 2, the increase in acid strength is by the units of 7.6. There's an increase in pKa by the value of 7.6. So the increase in acid strength is more. I'm sorry, I mean the decrease in pKa is more, which means the increase in acid strength is more. As compared to when you go from 2 to 3, the decrease in pKa is only by a magnitude of 3 units. So increase in acid strength is on similar lines to a lesser extent as we have expected. Because when we go from 1 to 2, what is the difference? We added one phenyl ring. So pKa decreased by 7.6, acid strength increased by same magnitude, okay. But when you go from 2 to 3, the increase in acid strength or the decrease in pKa is not to that extent as we have expected, because we added one more phenyl ring. So we expect a cumulative effect. So what is the reason behind that? That is the question, okay. So to answer that question, we need to understand that in the case of triphenylmethyl carbanion, what happens is, so this is the carbon So you have 3 phenyl rings attached to the central carbon bearing the negative charge. And because of the presence of these phenyl rings, what happens is that these hydrogens, their electron clouds, they come quite close to each other, and because of which they start repelling each other. There is lots of steric strain, lots of steric strain. And because of the steric strain, the energy of the system increases, which means that the stability of the system decreases. So in order to decrease this tension or this strain, what this molecule or what this carbanion does, that these phenyl rings, they go out of the plane and arrange around the central carbon as the propeller. Okay, so I can show you here. So they arrange themselves like this. So you can see this, that how they are arranged here. So let's cut it and paste it here so that we can clearly see that how they are arranged. So they are arranged in a way as a propeller. So they go out of the plane, and as they go out of the plane, so they are in different planes, the coplanarity is lost, because of which this negative charge, which could have spread to all the 3 rings to an equal extent, that coplanarity is lost. So delocalization is kind of hindered, or it happens to a lesser extent. It happens, but the extent of that delocalization is or the magnitude of that delocalization is decreased. Okay, so in the previous 2 carbanions, everything was in the same plane, so electrons they have the capability of jumping to the next orbital, but here, since they are in the different plane, so coplanarity is lost, because of which the delocalization gets decreased. So it did increase from going from B to C, but not to that extent. And the reason behind that is because the 3 phenyl rings, they have to go out of the plane in order to counteract the steric strain in the molecule. Fine. And this explains why the magnitude of the pKa decrease here is lesser as compared to this one. Fine. Let me know if you have any questions related to that. I will definitely get back to you. Thank you.